Okay, so in the previous lecture, we had asked this question that, uh, yeah, so we had asked this question that can we define a quotient group for any arbitrary subgroup of a group G, right? So the question was typically of this form that if N is an arbitrary subgroup of G, then is the quotient group G mod n well defined? Okay, obviously as a subgroup. Okay, sorry, I should say as a group. Um, In some books, G mod n is the notation used to define all the collection of all the left cosets of G in N. But the way we introduce this notation, it typically refers to only the quotient group. That is only the case where the collection of all left cosets form a group. Okay, so we will stick to that notation. The G mod n doesn't refer to the collection of all left cosets, but it only refers to the case where the collection of all left cosets form the quotient group. And we had defined a notation, an operation for the quotient group to be a group indeed, which was like if I choose any two elements from G mod n, if you recall the elements were of the form translation or some scalification of the denominator group of some sort. That is, if you choose elements from in the form un and vn, then the operation would give you uvn. Right? Like we had chosen this to be some fiber, this to be some fiber. If I project it back, it goes to U in some sort. If I project it, so suppose this is some fiber. Let me just quickly recall how we had discussed these cases. Okay. So we had chosen an element A out of the, you know, so we had chosen phi to be a homomorphism from G to some group H, with the kernel being this group N, when it forms a group indeed. Okay, if a group. So how did we construct this group? That was my question, which we had covered in the previous lecture. So this is just a quick recall. So we had chosen the kernel to be some K, let's say kernel K. Then what we did basically is that we chose X to be the fiber over A, right? We chose X to be the fiber over A, and then if I for all U in X, we showed that X is basically of the form UK, and typically we can also do this for the in case of the right cosets as well. That if I that is for all V in X, we can define X to be in the form KV. Yeah, so we have defined this to be the left cosets, this to be the right cosets, and these are indeed the representations of the fibers. Okay, so considering two fibers, so if XA we choose and XB we choose, then XA will be of the form UK and XB will be of the form some VK, let's say. If I project them back, they will go to A and B in the codomain group, right? If they are composed, they will form the group. They will form the element AB. If I project them back to G, they will come as the fiber over AB. Where a fiber over AB we define to be UVK, right? So if I choose two fibers XA and XB, so this has a representation of the form UK, this has a representation of the forms, let's say VK. So if I project it back, then it goes to A and B. If I compose them together, they form AB. If I project them back to G, bring them back to G, then it will give the fiber over AB, which I represent as UVK. So UK and VK composed together gives UVK. This was the operation we has defined for G mod K to be the quotient group. Now my question was that this complete construction was based on a kernel of some homomorphism, some predefined homomorphism. Can I do it directly with the help of some subgroup? Because indeed the kernel forms a subgroup of G, right? The kernel forms a subgroup of G. The kernel forms a well-defined subgroup of G. So my question is, can I do it for any arbitrary subgroup of G? We assume that we have no homomorphism in hand at this moment. We are only given a certain subgroup. So can we construct a quotient group directly out of that subgroup using this operation. Because now we are pretty sure that if I consider the collection of left cosets, that indeed the collection which will eventually form a quotient group with some well-defined operation, right? Because whatever we are working with here are some left cosets or some right cosets, whatever. Okay. So the answer which we had given is no. It is obviously not possible because there is something more to a kernel than to an arbitrary subgroup. Okay. There is something more to a kernel than an arbitrary subgroup. So what's that property, which is what we are gonna discuss today. In the previous lecture, we had given a proposition which will eventually lead us to exploring that basic property. So let me just quickly recall the proposition. I will not give the proof of it. I had done the proof of it in the previous lecture. Let me just write the proposition first. The proposition was in this form that if I choose an arbitrary subgroup of G, then the collection of all left cosets of G in N, sorry, left cosets of all N in G, it will partition G. Okay, the left cosets of all, sorry, the left cosets of N in G, it will partition G, right? If I ever said left cosets of G in N or the left coset of the group in its subgroup, then that was a mispronunciation. I wanted to say the left coset of the subgroup in the group. Okay, left cosets of N in G, partition G. That's the way it is said. That's the way it's said. Okay, okay. Furthermore, if or I should say UN is equals to Vn, where U and V are any arbitrary elements from G, then this happens if and only if V inverse U is in N. Okay, and so thus we can also say it in this form that UN is equals to Vn if and only if U and V are representatives of the same coset. U and V are representatives of the same coset. Clear? This was what we had proved in the previous lecture. Representatives in the sense you can think of them as U is in Vn and V is in Un for like that sort. So if Un is some coset and I choose an element in Un, then A is said to be a representative of Un in some sort. Okay, that's the case. Okay, yeah. So now we come to the main thing which we want to discuss today. Let me write it as a proposition again. So we say that if G is a group and N is a subgroup of G, let's start with that. Let G be a group. Let G be a group and let N be a subgroup of G. Then number one, the operation on the set of all left cosets of N in G, which we defined as UN dot Vn is equals to UVn, if you remember. This is well defined. This is well defined if and only if G inverse is in N for all G in capital G and for all N in N. Okay, that's the case. And the immediate second proposition will come in this sort, which is some sort of a carry forward from one, which is if this happens, that is if this operation is well defined, if the operation is well defined, then obviously G mod N forms a group, right? then G mod n forms a group, where again G mod n in this case will refer to the collection of all left cosets. Right? So then G mod n forms a group with the identity element of G mod n being 1G, sorry, 1n, right? And the inverse of any element from G mod n will be just G inverse n. If you prove this out, this is nothing. This is very trivial a statement. Okay. Let's prove it out. Okay. So what do we need to show for the operation to be well defined? First, let us choose the operation to be well defined. Let the operation be well defined. Operation be well defined. So in a way, if the operation is well defined, then if I choose any, so you have un dot vn to be uvn. So if I choose any two other such left cosets, say u1n and v1n, such that u1n equals un and v1n equals vn, then u1 v1n must equal uvn. That's the precise way to check out whether a given operation is well defined or not, right? But we can actually do that because we already know that if two left cosets equalize, if there is an equality between two left cosets, then the elements which are scaling the subgroup to form the left coset, they must represent the same coset, or they must represent the same partition, right? This was something we had proved in the immediate previous lecture. I had just given as a proposition which, right? Therefore, so choosing, so at least we need four elements, right? un, vn, which compose to give uvn, and we need to choose two other elements, two distinct elements, u1 and v1, different from u and v, such that un equals u1n, v1 equals v1n. We are to show u1 v1n equals uvn. So what is the other way we can do it? We can come up with this conclusion. If I choose u and u1 from the same coset un, because they will eventually represent the same coset, and I choose v and v1 from the same coset vn, because they will eventually represent the same coset, and we have to show that uvn is equals to u1 v1. So that is the precise way to show that our operation is, or that at least this operation is well defined. In the first case, we are assuming this to be well defined. So then we can say, therefore, if u and u1 come from un, v and v1 come from vn, then uvn equals u1 v1n. Okay, this is something we are given. Clear? Okay. So we are to show that Gn G inverse is inside n for all G in capital G, for all small n in capital G. That is what we need to show. Okay. What do we do is basically, so this is something which we are given, right? So we choose u to be 1, v and v1 to be G inverse, and u1 to be n. Okay. Then what does this give us? So this gives us that, so v is G inverse. So we have G inverse capital N is equals to n G inverse capital N, right? Okay. Now n is a subgroup, right? Since n is a subgroup, 1 is in n, therefore n G inverse is in n, right? Sorry, n G inverse is in n G inverse n, right? So if n G inverse is in n G inverse n, so, and n G inverse n equals G inverse n, so that implies n G inverse is in G inverse n. But that implies n G inverse equals to G inverse small n for some n1, let's say, for some n1 being in n. So if I just left multiply by G, I get G n G inverse to be equal to n1, but n1 is an arbitrary element from n, which is in n. So that implies G n G inverse is in n. And since n was an arbitrary element, G was an arbitrary element, eventually G inverse is also an arbitrary element. So this satisfies the thing which we require to prove, right? Okay. So we have to prove the converse. Okay, the converse. Okay. So what do we need to show in the converse? So exactly what we just said before trying to prove this. That is, if I choose, so we are given that un composed with vn is equals to uvn. This operation is, we require to show this to be well defined. So we choose u1n dot v1n equals to u1 v1n, where these two are same, and these two are needed to show, needed to be showed to be same. So if these two are same, then I can choose u and u1 from un, because they will represent the same left coset. V and v1 from vn, they will, they will eventually represent the same coset, same left coset, and we have to show these two equal. But the other way of showing these two equal is u1 v1 is in uvn, because if u1 v1 is a representative of this coset, then the left coset scaled by u1 v1 will also be same as uvn, right? Okay. So how do we go? So again, we choose u and u1 from un, v and v1 from vn, and to show that u1 v1 is in uvn. And what is the hypothesis we have? That G n G inverse is in capital N for all elements G in capital G and for all small n in capital N. That is what we require to show, right? Okay. So yeah, so if u and u1 are from un, then I can write u1 as un and v1 as vm, let's say, that n and m come from it. Okay. Then what is u1 v1? We need to show that u1 v1 come from uvn, right? So if u1 is in the form un and v1 is in the form vn, then u1 v1 is in the form un vm. But by associativity, I can write it as u n vm, which we can write as u v inverse v, or let me write it as v inverse. Okay. So u v, u v inverse nvm, because v inverse is nothing but identity. Then this comes out in the form uv, by associativity. This part we take together, that is v inverse nv, and you have m here. Now small n is an element from capital N, v and v inverse are elements from G, so this must precisely be in capital N by hypothesis, right? So which we can write as, so it's in the form uv some n1m, where v inverse nv is equals to n1 and it's an element from capital N, right? But m is also an element from capital N. N1 is an element from capital N. By closure, n1m is also an element from capital N. So it's in the form uv n2, where n2 equals n1m and is an element from capital N. But this is precisely an element from uv capital N, right? And that is what we require to show. Clear? Got it. Okay. Now if I talk about the statement 2, then we already know that this operation makes the set of all left cosets to be a group, right? That is something which we have already shown previously when we had started the construction of a quotient group using a kernel. Okay, this was the exact operation we had talked about. So showing that it's a group, it's obvious. Identity element also will come as obvious, because un dot 1n is equals to u dot 1n and equals to un. So immediately this forms the identity, because the existence of identity is unique, right? And if I start with the left coset un, if I compose this with u inverse n, because u inverse n, u inverse, the element u inverse is well defined because we're choosing an element from a group. Inverses exist in a group. So this will come out as u inverse n, right? But u inverse is identity, so it's 1n. I guess it's obvious from here. Okay, is it clear? So what do we conclude up from here? Okay, so conclusion. The conclusion is very obvious that if G is a group, and n is a subgroup of G, then G mod n is a group if and only if for all G in capital G and n in capital N, G inverse NG, or I should write in the usual way I write this out, because it will eventually lead to a confusion if I keep on interchanging what I write. G n G inverse is in N, right? Now, if you recall, we had used this sort of a notation when we had defined the concept of a centralizer or even a normalizer, right? So now it's a time to define such an element. Okay, so definition. Now that the main fact which comes up from here is that this is a property which is necessary and sufficient for G mod n to be a group. That's the specific case. So we need to define such a property. Okay, so definition is that the element G n G inverse is called a conjugate of n by G, or we often say that G conjugates n in a way. Okay. We define, now this is something which is already defined, G n G inverse to be the collection of all the conjugates of n by G. G n G inverse such that G is in capital G and n is in capital N. Clear? Or since we are already talking about G, let us not write this condition here. That's not appropriate. Clear? This set is called the conjugate of a capital N by G. This set is said to be the conjugate of capital N by G, right? Okay. Okay. So a subgroup capital N in G is said to be normal if for all elements small g in capital G, the conjugate of capital N by G, equals the subgroup N. Okay. We also say that in this case, if N is a normal subgroup, we say that G normalizes N. Capital G, the group capital G normalizes N. Okay. So that typically means also, if you recall the definition of a normalizer, that the normalizer of this subgroup N in G should equal G. So that's precisely why I say capital G normalizes capital G. Okay. So in that case, we denote it as NG. We also often use this notation as well, but that's not quite required. Whatever. Okay. So therefore, the fact comes out like this is, if G mod n, so I should say it in this way, G mod n is a group. That is, we have a well-defined quotient group for some subgroup n of G, if and only if n is normal in G. Right? Okay. Now, as we have defined the normal subgroups, there are some immediate observations which we have proved on our way. That is, theorem, let n be a subgroup of G, then the following are equivalent. N is normal in G. Number two, the normalizer of n in G is G. Because what is the normalizer of n? The normalizer of n in G is the collection of all the elements in capital G which normalizes the set capital N. And we have just seen that if n is normal, then every element of G normalizes capital N. Hence, it must equal the whole of G. Right? Number three, this is quite important, but you can show it on your own. That G capital N equals to N capital. Small G capital N equals to N G. That is every left coset of N in G equal to, or I should write in, every left coset of N in G represents every right coset as well of N in G. Okay, so the precise thing is basically that if, because every element in capital G normalizes N, so G n G inverse equals to N for all G. So that's precisely gives the fact. That is, the collection of left cosets actually equals the collection of all right cosets. So that is the thing why we eventually constructed everything for a quotient group using left cosets. Because at some point, at least I knew that we will be eventually coming to a right coset. So there is no distinction between the collection of all left cosets and the right coset when we are concerned about a quotient group. Okay. One more thing I should say here is that when I am writing this, I do not mean that Gn equal to Ng for all n in N. But this statement actually means that Gn is equals to N1G for some N and N1 in N. So G capital N equals to capital NG doesn't immediately mean that G, the elements of capital N commutes with the element G. It actually means that if I start with any element from the left coset, G small n, then there must exist some element N1 in capital N such that N1 G equals G. Okay. So commutativity is not coming directly out from here. That you must observe out. Okay. And so the next equivalent statement is that G mod n forms a well-defined group. Okay, with the usual with the usual operation which were defined. Number 5 is quite observatory. Observe that if I choose any element from N, okay, let's say N1, then N1 N inverse is an element from N. Sorry, yeah, is an element from N, right? Because this obviously comes out from closure, right? So if I N1 N1 inverse, sorry, so this is directly comes out from closure of N, but this is indeed an element from G and G inverse, because if I choose an element from capital N, that's eventually an element from capital G. So that means that the subgroup N is always inside the subgroup G capital N G inverse. Okay, clear? So if I just show that G n G inverse is inside N, that suffices to show that N is normal, because the reverse inclusion is obvious. Okay, the reverse inclusion is obvious. So this is another equivalent statement. Okay, so let me just add the fact that it's for all for in J capital G. One thing I would ask, show that, or I should say, at least I shouldn't be too sure up with this fact. Should say verify. Verify whether the set G and G inverse forms a subgroup of G or not. Okay, try this out. Is it clear? Okay. So now, we had done everything to construct a quotient group out of an arbitrary subgroup of a group G. Now the last question which remains in this fact is that while we introduce the concept of a quotient group, we relied completely on the kernel of some homomorphism, right? And in a way, we had observed that the subgroup or the, if I consider a quotient group G mod K, if I consider a quotient group G mod K, then this set K somewhat needed to be the kernel of some homomorphism, right? So now we are going to validate that point as well. That if I start with an arbitrary subgroup N of G, such that G mod N forms a quotient group, then this subgroup N forms the kernel of some homomorphism. Okay, so that is the exact proposition. Then this will completely validate our construction of a quotient group by specifying some homomorphism, which will be equivalent to constructing the same quotient group using some arbitrary normal subgroup of G. Okay, so the proposition is like this: a subgroup N of G is normal if and only if N is the kernel of some group homomorphism, obviously arising from G. Homomorphism arising from G. Is it clear? Okay. Because if N is a normal subgroup, then the quotient group G mod is well. Okay. So the proof of it, let's talk about. Okay. So we start with a homomorphism. So let phi be some homomorphism to G to some group H. What we can show is that if the kernel of this homomorphism is normal in G. Okay. So let kernel of phi be some K. We have already shown that it's a subgroup of G, so it's okay. Yeah. So we start up with some kernel. We show that it's normal. Conversely, we will choose some normal subgroup. We show that it's some kernel. So I guess that completes the proof. So we will show that K is normal in G. So to show that K is normal in G. Okay. Yeah. So what we need to show is that we will use the last equivalent statement for the normalizing, which is if I choose that is to show GK G inverse is inside K for all G in capital G. That will do it, right? So let G small k G inverse be an element from G capital K G inverse. What is phi of G small k G inverse? By homomorphism, it will become phi G, phi k, phi G inverse. But K is an element from the kernel, right? So phi of K must be 1. So it's phi G dot 1 dot phi G inverse. But then it becomes phi G inverse. But that's exactly equal to phi G inverse by homomorphism. But G inverse is again 1. So it's phi of 1, but phi of 1 is 1. That means the image of GK G inverse is also 1. So that means GK G inverse is in K. Therefore, G capital K G inverse is an element. So it's contained in capital K. This immediately means that K is normal in G. Clear? Okay. subgroup the converse. So the converse actually leads to a very useful and a very important sort of a homomorphism, which even which we call to be a natural projection or a natural map or a natural homomorphism, whatever you want to say. We'll see it eventually. So what we do is that let n be normal in G, then define the usual quotient group. I know that this is well defined at this moment, right? Because n is normal. So we choose a homomorphism from G to G model. Okay, because G model is a group, right? So the usual notation which we use in this case of a homomorphism is pi. Okay, that's the natural convention. Well, I will naturally define as homomorphism, so let me just abide by the notation. So pi G to G mod n is a homomorphism such that the homomorphism defined as pi of G is Gn. Okay. Then what is the kernel of this pi? Then kernel of pi. So by definition, the element of all G capital G such that pi of G is 1. But pi of G is 1 means, so it's the identity in G mod n which is eventually seen as 1n. Right? So this means that it's G in G such that Gn is equals to 1n. But we know that if Gn is equals to 1n, then both G and 1 must represent the same left coset. 1n is nothing but the left coset n. So G must represent the left coset n. That is G must be in n. So this implies the collection of all G in G such that G is an element from n. So eventually that's just n. Right? Because G intersection n is a subgroup of G. N is completely contained in G. Right? So therefore we have shown that when we start with a normal subgroup, then we eventually form out we can eventually form out a quotient group, and if this normal subgroup is eventually the kernel of some homomorphism, and if I start up with a kernel, then that also eventually forms a normal subgroup. Okay, this homomorphism is called a natural projection. Okay, so let me just give it as a definition. Yeah. So let G be a group and n be a normal subgroup of G. The homomorphism pi from G to G mod n by G getting mapped to Gn is called a natural projection. A natural projection, or more famously called a natural map. A natural map. Okay. Natural map of G onto n. You can obviously observe that this map is surjective. Okay. It might not be injective for obvious reasons because we can have multiple representatives from the same coset. Right? If I choose two elements G1 and G2, then they can represent the same left coset. So it need not be injective, but it's obviously on. Okay. Yeah. Okay. So we end this part of our quotient groups with one important observation. Which is we have eventually seen that the relation of being a subgroup is transitive, but being a normal subgroup isn't. Okay, being a normal subgroup isn't. That is the relation of being a normal subgroup is not transitive. What do I mean? We have observed that if n is a then that would imply N is a subgroup of G. But if N is normal in H and H is normal in G, that immediately doesn't mean N is normal in G. Okay, verify this on your own. Okay, collect subgroups which are normal in some subgroup, and that subgroup is also normal in G, but eventually N is not normal in G in a way. Okay, check this on your own. Verify. Consider the simplest examples of groups. I guess you can come out with some example out from there. Okay. So the construction of a quotient group is complete now. In the previous lecture, we will discuss some very important properties and some very important characteristics of quotient groups. And then we will be moving on to some more rigorous theorems on quotient groups. Namely, we start up with the Lagrange's theorem. Okay. So we do guys in the next lecture.